Okay, I'm talking to you all. Wonderful. Right. Homomorphic encryption. Um, okay, there's an example right there for you in a sense. You are perfectly free to take a picture of the QR code there on the screen, get all the information that you need about me. Bearing in mind that I did get my start in security in malware research, and that means that I know every possible way to get somebody to install bad stuff onto their computer. Now, yet another example, if you will, of homomorphic encryption. This really isn't an example. This is just weak encryption, of course. And ROT13 is the way that we hide, semi-hide things that we're talking about. And it's really just a weak form of encryption, so it's not really homomorphic encryption, because what we want to do with homomorphic encryption is to actually encrypt the data and still be able to use it for some purpose without decrypting it. It's not just easy decryption, it's use it while it's still encrypted. Now, a lot of people think that this is, really fantastic idea, and yes, I mean there are, some good things about it, but some people are going overboard. This was a news article that I came across recently, and they're calling it the Holy Grail of encryption. Yeah, it's got some good uses, but it's also got some limitations, which we will talk about as we go through here. First of all, homomorphic encryption is not a new thing. We have, in fact, been using forms of homomorphic encryption for some time. For example, how do we store passwords? We hash them. Hashing is one-way encryption. There is no way to decrypt the password. And of course, what we do is when somebody submits a password, we hash the submitted password and check it against the hash that we've stored. So we're not storing the passwords in an unencrypted form. They are encrypted. They can't be recovered, but we can still use them. We still have a use for that. So there it is. There's one example of homomorphic encryption, and we're using it all the time. Now, a few I don't want to push these. These are kind of bad or limited examples, but doing an exact search, which basically an exact comparison is what we've done already with the password hashing. But looking at the electronic codebook mode of block cipher, it is, of course, the weakest form of block cipher, the weakest mode for block ciphers. And that is because it, if you have the same data, you get the same ciphertext. And so, for example, if you're doing, simple graphics and that sort of thing, you can encrypt it using ECB mode, and yet you can still get a rough idea of what the image is about. So this isn't, well, this is just a weak form of cipher. But again, if we want to do exact searches or exact comparisons, and the block size is the same as our record size, we can use homomorphic encryption. Sorting as well. The Caesar cipher, when the ROT13 example up at the beginning there, or basically any encryption that uses mod functions, you can do sorting functions on a limited basis, and we'll talk about again a little bit later here about homomorphic encryption and fully homomorphic encryption. Many types of homomorphic encryption are give you a rough result, possibly a workable result, but not necessarily an absolutely accurate result. So we can get a rough sort out of a Caesar cipher or a mod function in encryption there. COVID-19 contact tracing. This was interesting. DP3T protocol just uses a random data beacon, and that actually contains no personally identifiable information. And that is why they can use this for contact tracing and still protect privacy. But that's only if you're doing the simplest form of contact tracing. As soon as you start adding location data, time data to the random data that the beacon comprises, that starts to present a problem for privacy as well. So again, different things here. The data beacon for contact tracing is a random number. It has no meaning. It's in a sense it's kind of perfect encryption because there is no original data there except for the random data. But again, this is not a really great example of what we want to use homomorphic encryption for. And of course, there's our QR codes for vaccine confirmation that you can prove that you have been vaccinated and you can do travel, you can get into restaurants, you can get into shows, stuff like that. And so you can take this QR code and present it and get into a restaurant and get into a gym, get into a movie theater, whatever it may be, try to travel on an airplane. And if you do use this QR code and try to do those things, you deserve everything that happens to you. So a better example here, voting in elections have been much in issue, both in your country and in mine. I am, of course, from Canada and therefore an untrustworthy alien, but we've had recently a federal election. We had a couple of elections provincially up here that have addressed issues of could we have online balloting, could we have machine voting, could we various. And I've been looking at voting systems for many years, and the various proposals that have been given have been pretty much universally terrible. I think one of the worst that I encountered recently was somebody who suggested that we use blockchain for online voting, and I just, for crying out loud, where is your head at? But Rivest, and this is the Rivest of the Ron Rivest, that is the R in RSA. He proposed this three-ballot voting system, and there's the some information you can get on. And by the way, I've fired into the track one chat and Q&A area some details and all the URLs that I'm using in these slides, so you don't have to madly try to copy that down. But the three-ballot voting system is really interesting. This is the first one that I've seen that really impresses me as something that is possible. Microsoft is bringing out something or proposing something called Election Guard, and from what they have said about it, I believe that it is in fact based on the Rivest three-ballot voting system. Now, the first thing about balloting is that we want it to be anonymous. We want people to be able to vote and vote privately, confidentially. Nobody should know what they're voting for. Now, I can't, go to, if you're interested in the three-ballot voting system, go to the, do some research on it, because what I am going to say here about it is overly simplified to the point of being problematic. But in any case, the three-ballot voting system, think for yourself of a ballot, regular ballot, in three parts. The first part being the names of the people that you're going to vote for. The last part being the check boxes where you're going to put your X. But the middle part of the ballot being a set of fairly random lines connecting the names to the different boxes. Now, that ballot is in three parts, and if you detach any of those parts, first, last, or the one in the middle, then you do not know from the two remaining pieces who this person voted for. Now that's as I say, that's overly simplified because the reversed system does this, but it does it mathematically, and it's very interesting. This can be implemented either on paper or digitally, and the voter keeps one of the parts of the ballot. There's three parts to the ballot. The voter keeps one part, and therefore that protects their anonymity. Now, because it's not the oversimplified example that I just gave, the mathematical relation means that they can, in fact, count the votes, even though it is, in a sense, encrypted. It is anonymous. And the three-ballot voting system also provides us with a number of things that we have not had before. You have non-repudiation of voting. The voter, having voted, the voting authorities, although they do not know the way that anybody did vote, they can tell that someone did vote. The voter is also able to verify that their vote was counted because they've kept this one piece, and they can use that to verify that their vote was included in the totals. The ballots are counted without being decrypted, and this is the way, of course, that part of the way that anonymity is protected. And I'm really impressed with this system. I think it's great. This is the first proposal that I've ever seen that I'm willing to consider possible in terms of implementation of online voting. But in addition, as I say, can be implemented on paper. We can take paper ballots, write them according to this three-ballot voting system, and still give people the anonymity that they currently have with paper ballots, the non-repudiation of voting for the authorities, and the verification to the voter that their vote was counted. I'm really impressed with this, and this is a very, very good example of an application of homomorphic encryption. Now, in broader terms, we need to address other functions. I mean, election is one function, but it's very specific. The thing with homomorphic encryption is that you have to decide what the function is that you're trying to accomplish in order to determine which homomorphic encryption algorithm you are going to use. And homomorphic encryption is not a single thing. You have to look at the purpose that you want it for, the function you want to accomplish, and that determines how you are encrypting the data in the first place. So it's not, you encrypt it with homomorphic encryption, then you can find other ways to deal with it. No, you have to choose what you want to do with it first, and that determines how you're going to encrypt it. Now, if you want addition and multiplication, and we'll look at some examples in a few slides here. If you're wanting to do addition and multiplication, and going back to the voting example, voting is just a special case of addition, right? So that numeric formula there, that is the demonstration of the laws of, or the principles of associative and distributed principles in mathematics. So any function f that fulfills that f a plus b equals f a plus f b, any function f might be the basis for a solution for a homomorphic encryption algorithm that we can use if we want to have addition and multiplication. And this is the way that you decide what is an appropriate homomorphic encryption algorithm. You come up with a formula. Whatever function is going to fulfill that a formula that describes what you want to accomplish, and any function that will fulfill that formula is the basis for a solution that you're going to pursue there. So these are specific examples, and again, these URLs are all in the chat channel. IBM has something called BGB, which addresses addition and multiplication. A lot of these are addition and multiplication. Microsoft has SEAL, again, looking at addition and multiplication. Google has an interesting one, looking slightly different at it, comparison and limited addition under private join and compute. Now, homomorphicencryption.org, that is a website that's got all kinds of references and resource materials there. And in the introduction page there, they've got all kinds of projects ongoing. And most of these are, you can see it's GitHub there. They're open source. You can go, you can get it, you can download the code, you can start playing with it yourself and look into homomorphic encryption and work with it. So now again, as I say, this is considered terrific stuff. This is, some people think it's the Holy Grail and that sort of thing, but what it isn't. Well, it isn't a thing. It's sort of like blockchain. I got to get a T-shirt that says, blockchain is not the answer, because everybody is saying, blockchain is the answer to everything. Well, it's, blockchain is not a single thing either. And so, as with blockchain, there are various functions. There are different functions that you're going to choose, and different implementations of it. So they've got different strengths and weaknesses there, and they will do different things. It's not universal, as I mentioned before. You have to choose your function in advance. The function that you want to come out with, the answers that you want to come out with, performing functions on the encrypted data, determines how you encrypt the data in the first place. And so if you want the comparison, you cannot use the same encryption that will give you addition. If you want addition, you can't use the comparison function. So the algorithms are going to be different, and you're going to have to choose the algorithm based on the function that you want to come out of. So we're not, it's not one size fits all. Just going into cryptography here for a second. In cryptography, we've got symmetric and we've got asymmetric algorithms. And the differences are, symmetric is the stronger. We know how strong symmetric encryption algorithms are. They're, pretty fast these days, but there's a problem with key management. You have to find a way to pass the key out of band somehow. And you've got to manage keys and the number of keys that you have to manage when you're dealing with, so on and so forth. Whereas asymmetric is not as strong, but key management is not an issue, because you've got that public key that you can post anywhere. You can put it up on billboards, you can put it in the phone book, doesn't matter. So, symmetric has problems with key management, but it's good, strong encryption. Asymmetric, it's pig slow, it's not very strong, but there's no problem at all with key management. So what we do is we have a hybrid system. So we're going to use the asymmetric crypto to manage the keys. And that's all we're going to do, because keys are relatively small in comparison to bulk data encryption. So, not a problem there. But we're going to use the symmetric algorithms for our bulk data encryption, and the asymmetric is going to handle our keys. Great idea. Unfortunately, for our current discussions here, we can't do that with homomorphic encryption. You are working directly with the encrypted data, and again, the data is going to be encrypted in the way that is addressing what you want, the specific function that you want. So, and also for homomorphic encryption, this is very mathematically intense. Asymmetric encryption is mathematically intense, and there's that's another reason that we only use it for key management. Is we don't want to use it for bulk data encryption. It's really going to be slow, lots and lots of compute cycles. Well, homomorphic encryption is going to be even worse here. There's going to be a lot of compute cycles here, and because we're dealing with the encrypted data when we're running the functions, we're still going to be requiring an awful lot of processing time. So this is going to be pretty slow. Okay. So the weaknesses here are we're going to have limited algorithms. We're going to have restricted functions. They're not going to be, absolutely everything we want to do. Or, if we find a way to do it, it's, we're only going to find that algorithm for that function. Again, there are going to be some things that homomorphic encryption just does not work for, period. As well as there are going to be issues where this is not practical because of the processing time. And if we are combining functions, the algorithms are going to be even more limited, and we're going to see weaker encryption probably if we try to add functions and try to build an algorithm that will address a number of these functions for us. We're probably going to be building algorithms that have a lot of weaknesses, are subject to a lot of arithmetic attacks. Again, recall from our bad examples earlier, the Caesar cipher is very weak in terms of the address space. And electronic code book is the weakest mode for block ciphers. So those weaknesses are just inherent in those examples. They are also going to be inherent in the examples for homomorphic encryption and the algorithms that we use there. Okay, CISSP question time. Which of the following is not an effective deterrent against a database inference attack? Partitioning, small query sets, noise and perturbation, cell suppression. And I love this thing because most people get fixated on the fact that no, you don't want noise if you're doing database work. And in fact, noise is a very effective protection against inference attacks. So, now, again, in terms of the weaknesses here, I mentioned this before, the accuracy. A number of homomorphic encryption algorithms only give you a roughly correct answer. There are, though, those who are pursuing what is referred to as fully homomorphic encryption, which will give you an accurate answer. And Gentry has a paper here, one of the first ones to formally address this issue of fully homomorphic encryption. Again, it's if you're interested in those, you can undoubtedly by this time find more papers and examples on that issue. But if you're into accuracy, you're definitely going to have to go for fully homomorphic encryption. Microsoft is using homomorphic encryption. And they have been making a big issue of this. Well, actually, no, it isn't. What they're doing is storing passwords in Microsoft Edge, and it's just hashing again. The password hashing the same way that we've always done it. And besides, Google Chrome has been doing exactly the same thing that they describe in Edge for years. So, yes, okay, it is true they are using homomorphic encryption in the same way that everybody else has been using homomorphic encryption for a long time here. So, okay, this has been a very quick but hopefully useful introduction to homomorphic encryption. Hopefully that has addressed a number of issues for you. Giving you an idea of what it is and what it isn't,